In our previous video, I explained a little bit about how a steam engine works. And although I used a locomotive as an example, the basic principle of a high-pressure steam engine is the same whether we're talking about a steamboat, a steamship, a factory, a generator, or a locomotive. What I'd like to do now is I would like to couple the idea of the indicator diagram with the basic operation of a high-pressure steam engine. Again, this is the type of engine that was coming into general use in the late 1700s and into the early 1800s. So let's begin with looking at our piston and our cylinder. Now remember, the indicator diagram has pressure on the y-axis and volume on the x-axis. And we're going to look only at one half of the cylinder at a time. Now you'll note that when we're starting off our steam engine, or in this case our locomotive, we are opening up the throttle valve, we are allowing steam into the cylinder, and we're pushing the piston. You'll note that the volume of the piston, or the volume of the cylinder, is increasing, but the pressure stays the same. Now, why would the pressure stay the same if the volume is increasing? Remember, when we're talking about a gas, when we allow a gas to expand, the volume increases, but the pressure and the temperature decrease. So this does not really behave in the way that, as chemists, we're used to thinking about gases. And the reason that the pressure stays the same is because the throttle valve is open. The engineer opens the throttle and pressure is coming in, or steam is coming in from the boiler at a constant pressure. So the pressure stays the same even though the volume is increasing. The cylinder is filling with steam, and that's pushing the piston and it's turning the locomotive's wheels. Now the piston gets to the end of its stroke, and you'll notice that at the end of the piston stroke, the pressure suddenly drops. And the reason that the pressure suddenly drops is now the valve gear is sending the steam in this half of the cylinder. Remember, we're only dealing with one half of the cylinder, is sending the steam to the atmosphere. So the volume stays the same because we're at the end of the piston stroke. The valve opens to the atmosphere and we are exhausting the steam. So again, the pressure is dropping. It drops from perhaps 40 to 60 pounds per square inch to atmospheric pressure. Now we're allowing steam into this side of the cylinder. We're allowing steam into this side of the cylinder, so the piston is pushing this way. And now you'll notice that the pressure stays the same. Why does the pressure stay the same? Because this half of the cylinder is still venting to the atmosphere. The volume is decreasing because the piston is being pushed in and causing the volume of the cylinder to decrease. Now at the end of the piston stroke, we're going to allow more fresh steam into the piston from the boiler, so the volume isn't changing because we're at the end of the piston stroke, but the pressure is increasing very dramatically from atmospheric to, again, from 40 to 60 pounds per square inch for a typical locomotive of the 1800s period. Now this is a very important date to remember. High-pressure locomotives were being developed around 1800. Sadi Carnot worked out the Carnot Cycle in 1824. So he was looking, or would have been familiar with locomotives and steam engines. And you'll notice that the cycle I just described for a typical locomotive is not at all like what you're going to see for the Carnot cycle. Now we'll talk a little bit more about locomotives and high-pressure steam engines in the next video.